So this is a recently open source project that we built at Uber to tackle some specific use cases that we had, which I'll go into, as well as broadly bringing incremental processing primitives onto Hadoop. And as we see, we'll see why we attempted all of this. So quick show of hands. Everyone's familiar with Hadoop, Spark in this room. How many of you guys have? OK. And how many of you guys have written a data pipeline, like in any MapReduce, Spark, anything? OK, awesome. Cool. So I'll try to go a little faster in like basic areas. Sweet. So first of all, I'm Vinod. So I'm on the data infrastructure platform team at Uber. So broadly worked mostly on data infrastructure for the past 10 years, give or take. Agenda for today. So we'll do a quick tour of data at Uber, like how we evolved, very, very short. Then we'll look into motivations for why we built this project. Get into some concepts that are key to the design of the project. Deeper dive into design and implementation. Look at few use cases, what it can solve, what it solves at Uber. And finally, compare and contrast with few other like approaches and data systems that exist out already. And talk about generally open source, how we are, what plans do we have, what's the roadmap, and how you can be a part of it. So data at Uber, I'm going to recap basically a story of roughly 3 years. So we started with, I think, as every other company started, and even like the company before Uber I worked on, all go through similar trajectory. So we had like unreliable data, so JSON data, like people talking to each other about what schemas are for the data sets. And we did not have, so unless a business grows, you don't know what the scaling points would be to some degree. So we had a lot of scaling problems. We did not have Hadoop yet. We had Kafka 7, and our data volumes were growing, and we were getting into multi-data center use cases where the merges weren't like, the architecture couldn't handle merging data between multiple data centers, and the data couldn't just flow that way. And again, we had like a lot of inefficiencies. We had several hours of delays in data, and we were doing bulk data copies from OLTP systems and stressing them in the process. And we just had one single choice for query engine, Vertica, which is what you use to query all of data. So fast forward, I think from our humble beginnings, we've gotten to a point where where we had this, we'll build like a beautiful bridge. So Avro is the lingua franca of data. This is again like something that comes from LinkedIn, a company that I worked for before, and works really well in practice. We enforce schema at producer side, so got rid of a lot of the reliability problems with data. All of our infrastructure scales horizontally. Nothing very innovative about these. We just rapidly moved our stack towards these technologies and like sort of caught this up to like kind of open source standards basically. And yeah, most of our data sets are now at 1 to 3 hours latency. We'll go into a lot of cases as to why, and Hoodie even tries to push this lower than 1 to 3 minutes. And we have multiple query engine support depending on the use case. And who are our users? Users are analytics, like bread and butter analytics. You want to do interactively analyze the data science, and data apps. So machine learning, detecting fraud, and trying to figure out safe driving patterns and so forth. And standard warehousing, ETLing, curating feeds from Hadoop onto like a warehouse like Vertica, or moving it into MemSQL for more real-time querying, things like that. And across these, the query engines we picked are Presto for most of the analytics or interactive querying use cases. And Spark is how we write data pipelines and generally complex algorithms which do machine learning or all of these like data crunching. And Hive is our like bread and butter way to build the data warehouse and express like traditional ETL batch pipelines. So motivations is what we'll look at next. So basically, the thing that we got from our users, we heard loud and clear after we put together like these query engines and sort of built up the standard Hadoop stack, is we want faster data across all of these use cases. Because of the nature of Uber's business is, since we touch a lot of the physical world, things change the physical world, and there is like a lot of business value in reflecting it quickly into our like kind of analytical or warehouse ecosystem as well. And one specific problem which I'm going to kind of use to motivate why we build the project is our bread and butter sort of trips pipeline. So what happens here is every 30 minutes, we get a bunch of new data, basically new trips, bunch of updates to existing trips. And the problem here is, so we do typically what you do in Hadoop to store data, which is to partition it by some time, like a day or an hour or sometimes some field. And the problem here was the updates. There was some new data, as you can see by the blue boxes. There was a lot of updated data for the current day, but the updates go well beyond the current day, even crossing few months even into the past. This means all the traditional techniques that people typically use to deal with this in Hadoop are, okay, we'll rewrite partition, we'll rewrite like the entire table. Those sort of things kind of don't work. And in fact, we actually started doing something which is the status quo in database ingestion today, which is, okay, you have a database, you somehow manage to scrape logs into Kafka. You get those logs, you kind of build a replica closer to your warehouse, in this case, a HBase table. And at this point, HBase is like effectively a read replica of your upstream database. And we also log these updates onto HDFS for sort of like safekeeping. But ultimately, what we do is we then snapshot this entire multi-terabyte data set onto something like Parquet, a file format, which is like really suited for analytics. And all downstream consumers then recompute their own derived tables based off of that. And needless to say, I mean, if we recompute on the full data for all of these data sets, we won't have capacity, right? So people do approximations and like guesses onto what portion of the data is actually changing. Going back to the previous slide, we make like assumptions on, okay, this table is only going to have updates till last week, like last 2 days, sort of things like that, right? So we kind of, but ultimately though, this snapshot grew and grew as Uber grew and grew. It went to like 800 executors, and it still took 8 hours to finish. And then, by August, we were like completely redlining. We'd thrown like 1,000 and 1,005 plus executors at this. Still was taking 10 hours. There's a running joke inside Uber that if we let this go like this, it'll become petabyte one day, and we can write a blog about how we have a petabyte pipeline. But but I don't think the ecosystem will survive. So we thought about, okay, fine. How do we fix this? Again, standard ways. Okay. Oh, why not query HBase? Yes, we can, except HBase is not actually really suited for analytical queries, like to be used as your prime time, query system, right? Because and it does not have support for nested data, something that we have, and something that Parquet and like ORC even supports really well. And again, doesn't come for free. In order to like have HBase support a core data set like trips at Uber, you need to actually operate HBase at a scale that is equivalent to HDFS. Unless you can do that, your HBase region servers are simply not going to be able to deal with the IO load. I'll go into a little bit more of this, sort of more down the line. And okay, why not use specialized analytical databases? They're like awesome for their purposes. A lot of them store data in memory. But in this case, what the problem we are solving for is we want to store all the data, like all the trips for Uber, right? So we can't keep all the data in memory. And again, we get into, okay, even if you put these two data sets into this specialized data store, you still have other data sets in HDFS you need to cross-join against, and it's not a very simple problem to solve. So, okay, what can we do here? Like, okay, let's not support snapshots. So give people only logs, right? Okay, fine, easy, right? Problem solved. But no, you only push the problem down to your user. Logs need to be compacted. So even Kafka has a log compaction feature, right? So, and if you don't solve this at this level, users are only going to merge these logs themselves inconsistently and inefficiently. And I don't think, like, we're not going to be able to control the efficiency of the entire ecosystem. Okay, can we do something with the data model where we can change this? The sad answer here is no, because fundamentally, if you have late data and you want it reflected in your derived tables, then yes, you need to deal with this. It does not go away. So then we, this forced us to come back to the real question that we were sort of dancing around, which is, okay, can we solve this directly on HDFS, like using, on Hadoop Data Lake? And what does it take to actually solve this, right? To answer this, we went a decade back because this problem is very familiar. It's not very new problem, right? How did RDBMS actually do this? If you take some changes coming into MySQL, you typically just update MySQL table. You pull some changes from a redo log. You do whatever transformations that you want to do, and you update it back into MySQL, right? So this is how the data CDC, the data integration space work even today. And I think the key differences here are we are dealing with petabytes of data across thousands of servers and columnar file formats. And so the problem is conceptually a little bit same, but I think the manifestation inside Hadoop is a little bit different, right? So we got our answer. So we needed to essentially support a storage abstraction on top of HDFS, which will let us do efficient upserts and then incremental pulling, where we know, okay, given a point in time, what was updated. So essentially streaming primitives, if we can support on top of HDFS datasets, then we'll be able to kind of just solve the problem that we saw now, but as well as sort of holistically have a chance to improve the entire ecosystem in terms of efficiency. So here is what we did. Got rid of the dump. It's like we don't have no intentions for a petabyte scale blog post. So we built an upsert primitive, which basically can achieve this upsert in 30 minutes, used 100 executors today. And we are moving towards 5 minutes with 50 executors. We'll talk about this more as we get into Hoodie. So once we have this, we built an, with some extra metadata tracking and whatnot, we are able to, it takes just 2 minutes to ask what are the trips that got updated or inserted in the last 1 hour. So now this gives the derived table, essentially the remaining 50 odd minutes to be able to build these derived tables as well. So most importantly, now these tables become more accurate. They're not like approximations anymore. So everyone can, so if you find a trip in the base table, then you can find the trip on the same derived table, right? So that carries a lot of value because these tables are actually, again, cross-joined in some cases. Ultimately, we have Presto users and our city ops people who are our major customers of our data. Very happy because now they get fresh data, and ecosystem-wise, we are using 10x executors. Okay. So at this point, what we've seen so far is like a manifestation of a problem at Uber, how we solved it. And I want to take a little bit of time here to motivate some of the more theoretical concepts in whatever we saw here, right? So to try to kind of understand this a little bit more in an abstract way before we dive into sort of like Hoodie and the internal guts of it. Okay, let's simply start with understanding a data pipeline in a very theoretical way. So it's ultimately, it just boils down to reading from a source, doing some transformations, writing it back to a sink. Whether you're doing stream processing, where you're reading from Kafka, doing stream processing, writing it back into Cassandra, Kafka back or whatever, or you're doing a standard ETL pipeline, or you're reading from Hadoop or writing it back into Vertica doesn't matter. It's the same kind of abstract problem, right? And then ultimately what you will do is a combination of these operations. Projections and filtering, very, very easy. Any engine can do this really well, row-based transformations. Aggregations and windowing are a little bit tricky, where it needs some stateful processing in terms of what are the window lengths and whatnot. And then when you join a lot of these individual tables, then things start to get really hard, right? And operationally, you have essentially these levers for a data pipeline. So this is directly borrowed from the Google Dataflow paper, which I think is one of the papers which makes most sense in terms of conceptually understanding a data pipeline. So essentially, you want all of this done at some latency and at some correctness or completeness of your results. And when we talk about correctness, there is actually a balance between latency and correctness, especially if you take late arriving data or joins. You want to join two Kafka streams in a stream processing way. It is a little bit tricky, but it's tractable. But if you do want to do a 6-way join, then it becomes much harder of a problem, right? So most people do the trade-offs where they kind of pick 2 out of 3. You can achieve all 3 if you want for simpler pipelines or by spending a lot more cost. Very common way to build data pipelines, Lambda architecture, right? So you have a speed layer where you do some of these more simpler processing, and you serve the simpler data, but at much reduced latencies. You may take a hit on completeness, as I said, in some of these cases. Then you do more complex transformations and more complete, maybe complete recalculation of the same results in a batch way, and then move it into another serving store. And a layer merges both, and that's I think been the norm for a long time now in terms of data processing. And there are some theoretical reasons why. But overall, what this has led to is there is a forced dichotomy here, where we are used to thinking about data pipelines as stream and batch. And I think in reality, it's actually a spectrum. Even at Uber, when we looked at our data pipelines, we have the 1-minute level ones. There are very, very few, right? There are very few where we say surge is 1 minute. We are recomputing surge and whatnot. But a lot of use cases straddle the 10-minute line. If you're doing dashboards, you may sacrifice your completeness a little bit to get more fresh metrics to see what's going on. And as you go more towards a completeness line, fraud was one of the motivating use cases to build Hoodie to begin with. So we have complex joins there. So we want to run a incremental job on Hadoop where we are detecting fraud, or we want to do faster ETLs, something where we are computing how much incentive a partner has earned. So those things need more completeness. It can take a little bit latency more, right? And then you have the classic batch use cases. But across the board, what we saw was, hey, we have for every streaming pipeline, we have 100 batch pipelines, right? So and there is enormous value in actually making sure we have faster batch data, and batch pipelines can run more efficiently and more quickly, so that we can things that don't need a lot of sub real-time latencies can actually move into the incremental part, and some of the expensive batch pipelines can come into the incremental mode. And that's, I think, from a business standpoint, that's basically where we are trying to achieve. We are trying to make batch more efficient and streaming a little bit. The cases where it needed 10 to 15 minutes, we move into this mode where we can be more efficient. So what do we really mean by incremental processing is essentially running mini batch pipelines, but in a streaming fashion. So when you run mini batch pipelines, you get higher completeness than your typical streaming pipelines. And since you do it in a streaming fashion, which means you are only acting on new input and you're able to update old results, you get faster latency than your typical batch pipeline. So effectively, we basically filled the gap that we were observing, and then made it more of a spectrum of choices that you pick based on your use case, rather than being a sort of a dichotomy, as I mentioned. And I'll quickly go through some of the reasons why we did this. So increase efficiency. If you run so take this example. If you have events coming at 10K per second, you want to count the number of events in the last 10 minutes at 15-minute latency. Then if you run a stream processing job, it's going to keep updating some result store like HBase or whatever constantly. But you can just run a job which takes 5 minutes in batch, grabs more resources. It can compute, do all the count merges in memory, and just one update, right? So on-demand resource allocation and lesser I/O are both like big wins. And again, we can leverage all the Hadoop SQL engines, columnar file formats like Parquet, and they already cover a wide range of use cases, as I mentioned before. And again, like we are simplifying the architecture. So you can run these more faster pipelines on the same batch infrastructure that you are used to building your, like all of these other tons of pipelines. So what do we need? Again, to just do this on top of your Hadoop stack is upserts. They help you modify process results. They are like state stores in stream processing. An incremental pull, which is, okay, you get a log of changes, and you can avoid costly scans to just know what has changed in a table. So with this, finally, we formally introduce Hoodie. Hoodie stands for Hadoop Upserts and Incrementals. It's a storage abstraction to apply mutations to a data set and then pull change logs incrementally. Basically implements both these primitives. It's a Spark library. So it scales horizontally just like another job. So that's a distinguishing feature in terms of we didn't opt to write for a storage system, separate, which has to be scale like HBase or something. Open source, you can find us here, and effectively, what this looks like is you take a change log, you upsert it into a large HDFS data set, then it becomes a normal Hive table, which you can access via Hive, Presto, or Spark. In addition, you can also do an incremental query, which will give you only the changed rows as of a given commit time. So if you're familiar with event time and arrival time concepts in stream processing, the change log is basically giving you data off of arrival time, and then your standard queries run off event time. So very high level, what Hoodie is you embed a Hoodie write client, which is like a Spark library, into your Spark job, and then provide an RDD containing the data that you want to store and index. So this data then goes into, basically gets indexed, where we map a record to a file containing the record, and then data files where we actually store these data sets, and then some timeline metadata to basically help us implement things like change log. So timeline metadata stores all the activities that are writes and all of the background activity, everything that's happening to a data store. So it's like a redo log. And how we actually store and index and lay out this data is what we call as a storage type. And then the part about reading data, then like I said, it can happen via Hive, Presto, or Spark, and this is what we call as sort of views. So so the idea is, again, storage types define how the data is stored. Then views then give you a few tables on Hive with different tradeoffs to actually read the data that you've written. So for example, we have two storage types. One is called copy on write, which we'll quickly look into how it's implemented. But it provides a read optimized view, which is essentially purely columnar backed by Parquet data. And it also provides a log view, which essentially implements the incremental pulling capability. But, so the one that we are moving towards in the future is merge and read. That gives you in addition to the other two views, it gives you a more real-time view where it lets you query on the more recent data and by merging the columnar and row-based file formats on the fly. Okay, so now we're getting we've seen the concepts and sort of why we built it, all the motivation. Now we are going to take a quick tour into sort of the design and implementation of these primitives. And I'm going to quickly go a little quick here. So feel free to swing by the office hours, and we can go deeper into any of these areas as you wish. So basic idea is we have a partition data set on HDFS, date partitioned. Let's take one partition and one file, right? So we have, say, a pure Parquet data set at this point. There are some updates that have to be applied onto this file. So all the copy and write storage does is we added an index to figure out where these updates should go to. And then we simply rewrite this file with the versioning so that with the new records added, rewritten. So essentially, we are versioning files underneath. And if you do simple math, if you have these many partitions, this 100 GB per partition, and we block align the files to 128 MB, which is sort of our HDFS block size. And we have 800 files per partition approx. And we have a workload that's spread across a single record that will touch these many partitions. These many files have to be rewritten every sort of 30 minutes, and it takes 20 seconds to rewrite one file. With 100 executors, this comes down to 24 minutes. This is basically the first absurd number that you saw. So now, this is copy and write, right? This gives you pure Parquet performance. The reason why we went here first as a first step was we are moving a big ecosystem towards a new storage format. So we wanted to make it very non-disruptive to the existing queries, right? So now, what we are attempting to do with merge and read is we're taking 10 GB batches, and we want to apply it every 5 minutes, right? We want to do more incrementally. So at this point, rewriting the file is not going to work. The write amplification is too high. So we introduce a log and attach a log to each one of these files. And whenever the log reaches a sufficient size, we do the same thing again, which is we compact the Parquet and the log, and we produce a new file, right? And goes on. So here we've cut down the write amplification, and we are only rewriting 8 new files in average based on how we run the compactor. And so it's going to leave a lot of data kind of uncompacted in older partitions, which are kind of not touched by queries a lot anyway. So we more aggressively compact the recent data. That's sort of what we do. And by this, we are able to bring the ecosystem into 5-10 minutes, which is great because a lot of our tools and a lot of the Hadoop SQL engines now have access to fresher data. Right? So I think I'm going to just quickly go over all of these. So index, again, it's very pluggable. It basically maps the record to a file. We have Bloom filter and something based on HBase. And then in terms of storage, we adhere to the Hadoop file system abstraction. So whatever cloud storage system, which is consistent, has same consistent guarantees as HDFS, and you can write files onto. We can Hoodie can store files there. Let me go quickly over these. And I want to I'll quickly go over the API. So in terms of a Spark job that you want to write, you initialize the Hoodie client with a context and some configs. Then you essentially say start commit. It's like a database, commit, opening a transaction sort of thing. It gives you a handle. Then you give it, like I said, RDD of records with the handled commit time. And then you can explicitly choose to commit the data. So when we say commit, this is by leveraging HDFS's sort of atomic move, we atomically publish the data to the query. So either a commit succeeded or it did not. The query will never see partial data. That's another key thing that we added to HDFS, where I think before ingest processes can fail in the middle of moving files, and there'll be like some data that could be copied while some is not copied. And then we support rollback. Since we have a notion of commits, we can roll it back. Cool. So we kind of saw the storage type a little bit. Let's look at the views quickly. Like I said, like sort of two major views in terms of trading off between data latency and query kind of latency or query execution time. The read optimized takes a hit on the data latency, while it is like really optimized for analytical or columnar queries. While the real time tries to takes a little bit hit on the query execution time due to the use of a hybrid of columnar and row-based data sets, file format, sorry. But it pushes the data latency down to a large degree, right? And log view is simply a special view which uses the metadata and just simply pulls records out of the storage. Cool. So let's go back to how these views are implemented, and like for this we go back to our old right slide. So a view is simply like a table in Hive, and if you know Hive, so there is an input format where you have two things basically. One is get splits, where it gives you the files that you want to read or splits you want to read, and there is a record reader which does the actual I/O with the file, right? So what we effectively have done is written custom input formats with override get splits and like get record reader. So the read optimized file does not even look at the log files at all, right? All it will do is it will group files by the ID and pick the latest version which is committed, which is like a commit. But the real-time table essentially is going to read the the latest Parquet file, latest accompanying log file containing unmerged changes, and then going to merge it on the fly, and then return the results back. So again, so you get both tables if you do merge and read. So if you can even join the read optimized table with the real-time table if you choose to. We are simply exposing two ways of like looking at the data, but and we're just organizing it data differently so we can provide both essentially. An incremental log essentially will look at the commit metadata and simply it knows where things got changed, and it's going to simply pull it with the metadata that we have. So this is like a benchmark showing for Parquet. The performance benchmark, like the goal that we set was no degradation from versus like a raw Parquet data set. This is the major motivation for copy and write. And as you can see, pretty much across all of our production queries, we are on par. And again, to explain the incremental log view a little bit more, going back to our example, the incremental log looks at the timeline metadata where it knows a single commit has touched what partitions and what files. And based on that, it can essentially pull across partitions very, very efficiently. Otherwise, you'd have to scan, say, the last year's data over and over again every hour to actually figure out what trip has changed. And that's essentially how we implemented this. All right, use cases. So let's first understand abstractly, like sort of where Hoodie can fit in. So like Julian was saying, we can use Hoodie to sort of quickly replicate an online database or Kafka or any online like log events quickly into HDFS. So your OLAP world is in sync with your OLTP world at like say 10 minutes. Then you can build incremental data pipelines. Once you ingested the data quickly, thanks to incremental pull, you know what has changed. So you can keep kind of running your derived or your ETL pipelines every sort of 10 minutes, whatever, and you can keep pulling new increments. And at this point, it just becomes a standard stream join or stream data set join in Spark streaming terms, or in old school sort of Varos terms, it's more like fact dimension joins, but effectively it's the same thing. You can choose to put tables either in a streaming mode in terms of whether you incrementally pull it, or you can choose to scan it as you would normally do. But you are now able to build these incremental pipelines with all the primitives that we provided. And so at this point, enterprise software, right? So what happens is there is a system which is very popular. Then it has some shortcomings, a ton of systems built around that. And then eventually there is a catch-up phase where a lot of these things are kind of pushed back into the original system. So in the spirit of that, essentially now, previously you come to Hadoop only for few hours of data, right? Because the ingestion is bulk and the data simply won't even be there. So if the data is not even there, you're not going to be able to process the data within an hour, right? So, but right now, since we're doing this, we can use a Hoodie table on HDFS as like sort of mainstay for most of our batch and near real-time use cases. Adoption at Uber. So we are powering all our main data ingestion into Hadoop via Hoodie. And this is happening every 30 minutes today, and we are doing every several terabytes per hour. And we are moving very aggressively towards less than 10 minutes in the next few months. And incremental ETL tables, we have a few ETL tables which are like, sort of like I showed, incrementally built off of Hoodie. And overall, from a more platform perspective, we've managed to reduce the resource usage by more than 10x. So the graph on the top shows you the latency difference between bulk load and what we were able to achieve with Hoodie, just with copy and write. So that number is going to drop even more when we do merge and read. And this is the overall compute savings that we gained by doing like incremental upserts as opposed to bulk loading. It's fairly obvious. So, all right. One of the reasons I was moving a little quickly was I want to spend a little bit more time on the comparisons. So what trade-offs are we making here compared to other systems, right? So before we go too far into that, let's first understand some like basic benchmarks. This is a recent benchmark produced by CERN in terms of comparing different Hadoop storage formats for scan performance. So as you can see, Parquet clearly still comes out on top. You can see the point I was making about HBase before. And then Kudu is pretty close to Parquet, but still there is, if you look at gzip, which is what we use, there is like a 2x difference still, right? And Avro is a row-based file format, as I was saying before. Row-based file formats may not perform that well if you put it against like a columnar file format. But here is where it gets more interesting, is the write rate. So writing files on HDFS parallelly scales really, really well, right? That we all know for some time now. So if you look at the write race, it's dominated by Parquet and Avro. That is mostly justifies our reasoning for building it as a job, something as a library which embeds in your Spark pipelines, as opposed to building a storage system, right? Both things which have storage systems, if you see, they suffer a little bit because, like I was saying before, unless you are able to scale your storage system as big as something like HDFS, it's probably not going to perform very well for write throughput. So with this, let's try to understand these, compare Hoodie with two similar systems that we get asked about a lot, and two, HBase and Kudu, two projects which I personally have a lot of respect for. In terms of write latency, HBase is a honest database, right? So it gives you milliseconds of latency. Kudu, I think, is more like Kafka-ish streaming, so it can stream data within seconds. And Hoodie, for now, we're targeting a few minutes of latency, right? Because we have a lot of things to chew at Uber to bring the world to even this point. So the HBase val is implemented by appends. That's what we use for our own logs too. Maybe down the future we'll sort of approach that. For now, you can assume 1 minute, 5-minute updates, 1 minute inserts. It's sort of something practically you can achieve. Scan performance, we saw this already for HBase, not optimal. Kudu has its own columnar format, which is optimized, which performs pretty well. But Hoodie sticks to the state-of-the-art Hadoop formats, and all of the work that has gone into these formats you get for free. And query engines, there's a HBase Hive connector, that's it. Presto doesn't work with HBase as far as I know. And Kudu, again, I think it works really well with Impala. There's a Spark connector, which I haven't used, so I'm not going to talk more about it. But Hoodie, we've been running it at scale with Hive, Presto, and Spark for over 9, 10 months now. And deployment, again, this is the key thing. Extra region servers, at least they're stateless. But for Kudu, you would need specialized storage, and you have to essentially you have to operate a mini HDFS level of deployment. And this is where Hoodie for us was really handy, because we had a ton of Spark jobs and the ecosystem. So we just wanted to drop in a library and a data source where you can save data incrementally and read data incrementally right on top of HDFS. Given this, most of these are operational kind of advantages, right? But there are very functional key features that we built into Hoodie. And most of them, so multi-row commits. So Hoodie, by nature, being a mini batch or a micro batch system, does multi-row commits really well. You can roll back multiple commits. If you try to do this on top of HBase or Kudu, you have to manage how you are going to you have to either do this outside yourself, which can be tedious, and in some cases not even possible. Incremental pull is again something that we designed ground up to be able to build incremental pipelines for. Automatic hotspot handling. So anytime you put a lot of production pipelines, data will skew in different shapes and forms. So one of the reasons why we take that extra time there is to basically, we do hotspot handling where we try to size the files on HDFS and things like that. So we take that little bit of extra latency, do these things well, so we can scale as an ecosystem much better. We can drop pipelines into production and they kind of fly. And finally, open source. Hoodie is a very young project, and we're looking for contributors, and we have a few companies who are playing with it. Shopify is trying to use this for database ingestion into Google Cloud, and we have early interest from multiple companies. But engage with us on GitHub. Look for beginner tasks. Check out our tools, utilities. Please make suggestions. And we are indeed hiring for Hoodie, so if you're interested, you can take a look at our job posting as well. And in terms of what you can expect when you engage with the community, we have the merchant read project, which is kind of nearing completion, but there is still a good chunk of work in terms of productionizing it and whatnot. We have the global index project to build a faster index. Right now, we use Bloom filters to kind of implement our index, so we are looking at other ways to sort of make it faster as well as more global. And a Spark data source is long-term due. We just don't have resources to put into it. And Presto plugins, where we can take advantage of the index to do kind of point lookup queries very well. That's also something that we would like to do eventually. And finally, a beam runner is something that we are looking at to essentially, going back to our slide, we want to have a processing pipeline abstraction and have the user simply express the latency and the completeness, and the platform figures out what engine it can run, whether it's going to run in some streaming engine or a standard batch engine, or on the Hoodie incremental primitives based on the cost that we can offer this to this pipeline. So that's sort of something that we want to do and kind of build at Uber. Finally, takeaways. So Hoodie fills, we think at least, it fills a big void in Hadoop land by adding a standardized way to do upserts and kind of get faster data. Plays well with the existing Hadoop ecosystem. Hadoop is not going away, and so building this on Hadoop gains us a lot more velocity, in my opinion. And it's designed ground up for incremental processing. For example, incremental pull is something that we thought about very deeply before we got into the implementation. That's pretty much it.
Thank you, Vinod. So we have time for a few questions, and after that, we can do office hours. Do you have any question?
So my question was on when you're bringing in the incremental files, you have the original file, and then you have the second version of that, which is has a second. Is that a full, I guess, HDFS file, or is that a abstraction above that? And if it's an abstraction, do you ever kind of compress it to just a raw HDFS file?
It is a full HDFS file.
Okay.
So the abstraction is just the log. So essentially, if we wait till, say, you fill up 128 MB of the log, then we merge them and then write a new Parquet file. So things like it keeps going on. The compactor picks the file group with the largest log file and then decides to compact that.
Okay.
That's your second question for the conference. You get 3.
So suppose I have a large data warehouse already on the Hadoop and a Hive metastore. So if I want to use your framework, so does that mean I have to reprocess the whole data to leverage this?
So you have to rewrite it definitely because we have an index. But so the way we've done it is we wrote a utility to scan the first table and dump it in the Hoodie format. Then from there on, you can do this incrementally. But the short answer is yes.
But what about the history data? So you have to reprocess them.
So the answer is basically there's devil in the details. If you are very sure that your old partitions are not going to be in play, like they won't get updates, inserts, then you can just do it for the recent data moving forward. But the minute that you have an update to an unconverted partition in Hive, then Hoodie is not going to be able to work because it does not have the indexing information or anything to figure things out.
Okay. All right. Thank you.
Hey, so first question is about kind of the explosion of files in the HDFS cluster. So at Airbnb, for instance, we have an average block size that's pretty small. And if we were to use that, I think that would be probably even worse. And we've seen strain on the name node. So I'm curious to see if you've experienced some of that. And then second question is around whether you guys provide new SerDes, I would assume, I guess, for like Presto and Hive. And whether, I guess you might want to query the same table with different SerDes now, right? So do you have a SerD to read kind of the latest or an incremental SerD? So I'm curious as to how that works.
Okay. All right. So first one, files. So we do, so just to something that I went quickly across is we do clean the old versions. We do like garbage collect them. So it won't infinitely grow. But you're right, in general, we experience this explosion of files. So that is also one motivation for merge and read, is so that we can have a much bigger base file and a log file. So I think that's one of the motivations for even building this project is to abstract the storage layer. So does it make sense? That's basically the answer I have. It's manageable right now, but we want to get it to a point where, like, if you want to store, so we are, I think, going to soon go from petabytes to exabytes. So if we do that, we want a deterministic formula and a library which implements that to say, if I want to store this many petabytes on HDFS, and this is how you do it. And our bet is merge and read is how we are going to balance the file sizes and everything. And the second point is, so right now, so we still stick to Parquet SerD, but the input format, we've subclassed the Parquet input format to simply filter the files. For merge and read, we do that and also do the record reader, but the record reader ultimately converts it back into the same Parquet SerD. So Parquet is still primary. So again, we haven't had a very strong request outside of Uber to support a new file format. But I think we can simply write 2 more file formats and go there. So the incremental pull, the way we do this is same input format, but you set a Hive session flag to say mode incremental. If you do that, the query goes into incremental mode. There is a Spark client, which lets you do it very natively. Those are the 2 ways that we have incremental.
So can you do joins on 2 Hoodie streams?
Sorry, come again?
Can you do join on two Hoodie streams?
Yeah, you can. So it's just a Hive table at that point.
So if you do time join, then the two streams has time offsets. What do you do? Like,
So if they are not aligned,
they will not be aligned perfectly.
okay. So, okay, something I want to clear up is Hoodie does not change any fundamentals of computing, right? Like no impossibility results we have overcome. So the common technique people employ is when two stream joins, when they're not aligned, Hoodie can at least give you a look back window where if you say you always join the last 2 hours of data, and as long as you can estimate that, hey, these two streams won't be out of sync for a maximum bound,
Yeah,
you
that
can
makes
do
sense.
this. And we have systems in-house which track completeness and latency at 10, 15-minute intervals. So we query that system and sort of do these
Yeah,
queries.
I think that answers my question.
And that will be the last question.
I'm just wondering how tied you are to changelog sorts of data coming in as opposed to just sort of general Kafka streams of events and processing something. How strict are the time limitations?
So we view Kafka streams as just a subset of changelogs. So there is an insert API. So if you do inserts, you still get incremental pulls. So our Kafka data is also going on to Hoodie right now. Does that answer your question?
Roughly.
Okay, so let me give you a motivating example. So there are big Kafka topics which are 2 terabytes, like whatever, several terabytes a day, right? At that point, it's the same problem again. If you are scanning that one partition over and over again for finding out what are the new events, you're going to waste and scan, repeatedly scan and waste I/O as well. So the incremental pool still helps in those cases. That's a short answer.